Hey everyone, so today we're just going to do a quick mini lesson about power, specifically power related to circuits. Alright, so power, and remember we use the symbol capital P to symbolize power. So you may remember we talked about power when it came to energy. We said the amount of power is the rate of energy transfer over time, so the change in energy over some time period. Now we can relate this to circuits, right? Because we know that in a circuit, if we're trying to compute power, well, we're dealing with electric potential energy with the circuit. So if we're trying to find the power use of the entire circuit, or maybe just the power use of one element of the circuit, if we know the change in electric potential energy going on, let's make that a little bit clearer. There we go. And the time, we can compute the power. Right? Now, those quantities, when you're dealing with a typical circuit, are going to be difficult to measure, right? If we're able to measure something, typically it's going to be current, voltage, or resistance, right? So maybe we can maybe derive a formula here for power that's in terms of voltage or potential difference, current, and resistance. So let's see if we can do that, right? So we're basically dealing with change in potential energy over time. Well, if you remember, we do have a relationship for change in potential energy. We know that voltage, or potential difference, is defined to be the amount of potential energy available per unit charge. So we have this relationship here. So we can rearrange this, and we see that our change in electric potential energy is going to equal to our charge multiplied by our voltage. So using this here, let's just take this and plug it in up here. So now we have an expression for power is charge times potential difference divided by time. Right. So looking here, now we have one quantity we typically deal with, right? Voltage. Right? But we have Q over delta here, or here. Oh, man, I can't even speak. Q over delta T here. And Q over delta T, that should hopefully sound pretty familiar. Remember, when we're dealing with circuits, there's basically only going to be two quantities that deal with time, one being power, which we're talking about today, and the other was current, right? The current amount of current is the amount of charge per unit time. So effectively, what we have here is current. So you have current multiplied by voltage. So kind of, long story short, we can compute the power in our circuit to be the current times potential difference. So this formula is useful because if we want to find, let's say, the power for an entire circuit, how much power it uses, we can take the current for the entire circuit, effectively meaning the current running through the battery, times the potential difference of the entire circuit, i.e. the potential difference of the battery. We could also find the power used by each circuit element individually. So if we're dealing with, let's say, a light bulb or resistor, right, we are losing kinetic energy there and dealing with electric potential energy, so there's some power used there. So for like, example, a light bulb, it lights up, right? So we know that some energy is being converted there, or transformed, I should say, into light energy. So we can compute the power of a resistor or a light bulb or something if we know the current running through it and the potential difference across that resistor or light bulb. Right? So this is one equation we found here, but we may not always know the current and potential difference for whatever we're dealing with. Maybe we know information about the current and resistance instead. Luckily, we can apply Ohm's law to help us out. Right? Delta V is I times R, right? Because we can basically do some substitutions here. So for example, we can literally just plug in for delta V I times R. So then we have that power is going to be I times IR, giving us I squared multiplied by R. We could also do this, but rather than, we can rearrange solving for I instead perhaps. So that would be current is voltage divided by resistance. Right, so plugging that in, power is going to be delta V over R times delta V, giving us V squared divided by R. So we have effectively two other equations we could use depending on what we know about the problem. So really there's three different ways you could solve for power, applying essentially Ohm's law to this equation here. So let's look at an example. Let me scroll out a bit. All right, so we have, let's say, two resistors. One that has a resistance of 2 ohms and one that has a resistance of 3 ohms. And they're both connected to a battery, excuse my typo, with 12 volts of potential difference. So let's find the power delivered by the battery and the power transferred out of the circuit by each resistor if the resistors are connected to the battery in series and in parallel. And then after that, we have another question, but let's look at that first. So situation A, we're told that we have a circuit that has 2 resistors in series with the battery. So for sketching that out, here's our battery where we have the positive end up top. That's where we draw the long line connected to, let's put one resistor here, maybe one resistor over here. And these are in series with each other because they're in the same wire and they have the same current running through them. So we'll call this guy up here resistor 1, this one down here resistor 2. And we know that the potential difference of our battery is 12 volts. We know that resistor 1 has 2 ohms of resistance and resistor 2 has 3 ohms of resistance. Right? And we want to find the power transferred out of the circuit by, first power delivered by the battery and of each resistor. So battery, each resistor. Circling that, so I remember to do that. So there's two ways we can go about doing this, right? We could find the power for the whole circuit first, or each element individually and add them together. Let's kind of solve for the total power of the circuit first thing, then each element. Then we can check because we will expect the power dissipated by each resistor here to add to be the total amount of power lost by the circuit or used by the circuit. So let's see, we have a variety of ways, right? We can solve this. Effectively, we're going to be using P is IV, right? So if we know, well, we know for our battery that this delta V is 12 volts. So this equation here is saying, well, if we knew the current running through our battery, we could solve this right off the bat. Well, I don't know the current, but looking here at 2 resistors in series, we can very quickly add those together properly, which here we'll be just adding them together and find the resistance instead. So why don't we, instead of using IV, use V squared over R? So if we do that, we use our 12 volts here, square it, divide by our total resistance. Because these two are in series, it's 3 ohms plus 2 ohms, giving us 5 ohms. So the total power of our circuit is going to be 144 divided by 5, which gives us 28.8 watts is P total. All right, so now let's find this for, find the power used by each circuit element. All right, so for the circuit element, we could, sorry, I lost my train of thought. So we're solving for each circuit element. Man, okay. We could use, if we knew the current running through it, we can use this equation. We could also use V squared over R, or we can use I squared times R. Let's solve for the total current here. Right? We could also solve for the voltage drop over each. But let's deal with solving for current. All right? It might be simplest to use that equation. So if we want to solve for the total current of the circuit, we use Ohm's law. So let's say the I total is going to be the voltage provided by the battery divided by R total. All right, so it's going to be our 12 volts divided by our 5 ohms, giving us a current of 2.4 amps. And that's throughout our whole circuit because we don't have any wires splitting into other wires or anything. That current is the same throughout the entire circuit here, so it's through each resistor as well. So if we're solving for the power dissipated by resistor 1, right, we can do, let's say, I squared times R. We'll use that equation. So that's going to be the current running through resistor 1 times resistor 1 value. So that's going to be our 2.4 amps. We square that and multiply by resistor 1's value of 2 ohms. So let's see, 2.4 squared divided by 2 gives us 2.88 watts. That's for power of resistor 1. All right, I'm going to scroll a little bit more. Give myself a little more room to do the same computation for resistor 2. Right, which has the same current running through it, since they're both in series. But its resistance is 3 ohms. Oh, wait, did I do math wrong? I did math wrong. My calculator, I hit divide instead of multiply. Rookie mistake. All right, let me try again. 2.4 squared multiplied by 2. I apologize if you were yelling at your computer screen. I would be right there with you if I was watching myself. Ohms. Oh my gosh, I can't do anything today. Okay, this is in watts. All right, let me breathe. All right, power of resistor 2. We've got 2.4 squared times 3, giving us 17.28 watts. All right, we can do our check, add these two together. So 17.28 plus 11.52 gives us 28.8. Yay, what we expected. All right, so let's do a similar thing. Oh, let me hurry up since I only have 15 minutes for this video with this recorder. Situation B, we're dealing with 2 resistors in parallel. So I recommend you try this on your own and see if you end up with the same answer I do. All right. Okay, so again, same thing going on. So we have our potential difference of our battery being 12 volts. Resistor 1 is still 2 ohms, and resistor 2 is 3 ohms. All right, let me scroll up. All right, so solving this quickly. Let's find the total resistance of the of our circuit here, because we're going to use that to find total power. These are in parallel with each other, so we take 1 over the resistance we're trying to solve for is going to be 1 over 2 ohms plus 1 over 3 ohms. So we take 1/2, add 1/3. All right, that gives us 5/6, so 5 over 6 ohms. So our total resistance, our equivalent resistance for our circuit, is going to be 6 ohms over 5. All right, so the total power by our circuit, let's use P is V squared over R. All right, so it's going to be our 12 volts squared divided by our resistance of 6/5 ohms. So that gives us 144 divided by 6/5, which is 120 watts. Ooh, significantly more power than the previous situation. All right, so now let's compute the power dissipated by each of the resistors. So we've got, I'm running out of no time at all. Geez. All right, skipping over a tiny bit. So we can compute the power as V squared over R, and since we're dealing with each loop, the resistor, there's only one resistor in each loop we're looking at, so all 12 volts get dropped off in each resistor. So again, dealing with V squared over R, we find that power dissipated by resistor 1 is 72 watts, and by resistor 2 is 48 watts, giving 120 total like we expect. To figure out how the brightnesses compare, we compare the rank the powers. The more power, the brighter it is. All right, my 15 minutes are up. All right,